Nice rest. Austin, you're doing analytical labs next year, aren't you?
Yeah.
So you two are going to be in the same lab. So. Oh no, they probably will be. Hey, wait, question. Are you gonna stay on track with the inorganic one though?
Mm-hmm.
Okay. Because that one has no prereq other than the co-req lecture.
Yeah. Fall of next year is going to be a lot of labs, but
That was me this year, or this semester. I had 3. That's a lot of reports. There's a lot of biofilms. Basically, yes.
I have at least 30.
Huh?
At least 30. See, I don't know.
Yeah, it does. That's my.
No.
You told me you, as a you don't like it. You know, obviously I'd be surprised if she doesn't.
Pretty good, how are you?
Because that's like the majority of high school like chemistry I remember is inorganic because it has color changes and stuff. Like that's the one you will, I feel like you should have the most knowledge in.
feed up for
It's really, really low.
Yeah, because like doing organic chemistry with them, you know, it's like you don't get any of these attached with no color change or anything.
Yeah, I expect it to phase
Oh,
or
would
change
you?
color.
Which is
I'll do that.
inorganic lab. Mix these two metals together.
It's
One's
like
red and
really,
one's
really
colorless.
useless.
You know, we get green.
Most type of relaxation nowadays. I don't know, maybe for others it's
I mean, that's
What's
that's
that?
all I remember.
really useful on a cell phone.
Oh, yeah.
Oh,
Gen Chem labs.
I don't know if it's
Doing
much of a
copper
relaxation.
sulfate and stuff.
Yeah.
Probably
Colorful
stresses me out.
solutions
more.
and
My
stuff.
general chemistry class was boiling water. That was our first lab.
Well, other than that,
She's like, boil this, and it's water. And she's like, no. Yeah, it's water.
what? Then the finals are within 1 month. That'd be yeah,
that's a good one.
Let's see. 2 tests.
Fun already. It's almost o'clock.
well, I mean, because that week is the
Back to back.
presentation.
Yeah. You have to relax a little bit at least now.
We don't have
No.
the class on
Another
finals.
test.
I have an inorganic test on
I
Monday, but I
have
have an
the
inorganic
actual
homework due
finals.
Wednesday.
Oh, okay.
And the last, I haven't started it, and
Lecture,
the last time it took me
analytical.
like 20 hours
Geology.
as a group.
Oh.
Biochem.
Okay.
Biochem, geology, or Thursday, Friday.
This one's supposed to be harder.
Thursday's biochem, and then
Everyone
geology at
was
8 a.m.
4 or something. Nobody finished it. It was
English was like Monday.
Canadian Games on Thursday.
What is about British scientists? Do you hear some news like British scientists found that coffee prevents you from whatever disease or some strange things? Does it pop up in news? No? Okay, then there will be no jokes, but today today we will be exposed to British science.
British science.
Because we will have 2 lectures based on the textbook from Imperial College London about your degree of advance in physical chemistry. So, in some sense, it is an option for second opinion. If you do not believe me, what I tell, you can just look there. Because so we will try to follow our goal and see how oscillator oscillates on the pen and paper theory. And in British science, it is one of the assigned homeworks. I think it is too much, so we'll do it in assigning 2 classes, plus whatever preparation time we spend for this. And Before we go to British science, or science at all, please have a look on the possible subjects for independent research projects. You may have seen it. I was sending it as an email, and I will distribute one copy for each for your memories, and then we'll let one copy to circle around, where by the end of the meeting you may identify your preferences. So you may, yes?
Side question.
Please.
What are the odds that we can move the homework due date from Wednesday to Friday?
Huh?
What are the odds we can move the homework due date from Wednesday to Friday?
I made my little experiment. If the homework due date is on Friday, then no one comes on the Wednesday night session, or the attendance correlates.
Oh, really?
Yes.
I mean,
But-
it's only for you, doesn't know.
Well, some of you are coming no matter what, some of you are not coming no matter what. But those who are intermittent may observe the correlation. So, in some sense, homework prevents majority from, well, not majority, but substantial part from coming there. If there will be democratic vote of majority, we can postpone anything. Postponing due date, no problem, but it will not delay the assignment of a new homework. Would it be a good deal? Or are you not happy? Well, I'm flexible. Give me signals by email and I'll make vote on this opinion electronically. So let me put a little, well, star is reserved by some of you. So some symbol. So either write your preference near the question, or if you are too busy and do not have time to write your name, you can just connect your name with the subject by an arrow. And more than one choice is fine. Also, overlapping choices also are not a problem. There is a chance to make each project unique. So I want this copy back, and the rest of copies is just for your information. Okay, so who we are and what are we doing? It is a physical chemistry course. We are trying to predict future, predict observables, and right now we are looking on the oscillatory motion, which is appropriate for interatomic distances, for solving vibrations, for plasmons, for many things. But now we are looking only for vibrations, and you do see in these handouts what is going on, how the question can be formulated, and on the next pages how it is answered. The textbook thing is a little too dense. I hope that I will loosen it and make it more comprehensible. But if you like dense saying, you don't need to listen to me. So this is the homework that Brandon was asking Brian to postpone. This is based on the motion based on the motion that we predict in the labs. So if you do tiny modifications to the code, you may answer most of the questions from the homework. And the question is how the width uncertainty of the wave packet in the harmonic potential responds to the time. So there were several hypotheses, and you may address it verbally what is going on. So you see that, well, I will not take your bread and explain it myself. Really? So right now you do have a chance to, it's mismatch of fonts, but those are your names, and here is the list of subjects. The subjects can be fine-tuned, but some of the input towards where your interests are is really important. So you do not do assignment, but you follow your own interest. And hopefully by this time you already developed some. So two big classes is, everything is one-dimensional quantum motion. But under this one-dimensional quantum motion, you can understand either literal Cartesian position of electron hole, or you can understand reaction coordinating. So substantial amount of people with chemistry major select something from here, which can be combustion, catalysis, multi-step reaction, enzymes. Also, the potentials can be designed either by simple mathematical equations or just by step functions, or they can be borrowed from ab initio, where the student or postdoc helper may help you with happiness. So other subjects are different potential surfaces for different electronic configurations, which is most challenging but most innovative with potential for true life research, a little on angular momentum, and a little on electron-hole interaction. So if you are still in doubts, at least identify general direction. And then you can fine-tune what is your specific project.
The Marcus theory one is the looking at like a metal complex and how the ligand interacts with the metal center, kind of with the electron clouds, correct?
It is how the original Marcus theory is for rate of electron transfer between donor and acceptor, with understanding that upon electron transfer there is a substantial reorganization of interatomic distances or solvent polarization.
Okay.
So I think lecture study 3 didn't have any new material. So not much intentionally, but I was feeding you with boring, torturing mathematical content, promising that at some day we will see benefits and understand properties of real physical systems. Now we are approaching it very, very close. And the anchor that brings us there is a coherent state, which is eigenstate of the annihilation operator. Right now, I am not presenting anything new. It is what we did before. So we are developing this mathematical concept that if we find eigenstate not of the Hamiltonian, as people typically do, but eigenstate of the annihilation operator, we will get something really valuable. And in the past, we did apply annihilation operator to the lowest state, eigenstate of Hamiltonian, to find it. It was our trick. And now we are trying to find it to any state. So here is the representation of an any operator in the basis of eigenstates. Here is the annihilation operator, some unknown eigenvalue, and our question is to find this expansion coefficient. So the annihilation operator promotes from one eigenstate to a lower eigenstate, and if we plug it in there, we can practice our skills in series summation operator algebra and identify that bra meets cat becomes delta function, and then this summation meets delta, and they both get removed. Also, there is one trick to change the summation where summation starts, just offset it by 1, and then we arrive to, it's the same eigenvalue equation. C sub n is unknown. And now on the left, you have eigenstate n inside the summation, and on the right, we have eigenstate n inside the summation. So such notation will be correct if expansion coefficient in front of this n is equal to expansion coefficient in front of this n, right? And what have we seen last time? Is that here the index of eigenstate is the same as index of expansion coefficient, and here the index of eigenstate and index of expansion coefficient are different. This is a promise. So if we set up this equation between expansion coefficients on left and right, we do see that the expansion coefficients of nth and n plus 1 order are not independent, they are connected to each other. In general, such relations are called recursion. If we would have a year for this part of the course rather than half a year, we would do expansion coefficients to find eigenstates. It is based on the similar idea, but believe me, it is painful. So what does it mean? If you have index expansion coefficient n, you can find the next one, right? So why don't we try to start with the lowest one and then escalate and find all the rest. So I'm done with recalling, remembering, reviewing what we did last time. And now we are expected to come to a new material. So if we do have C sub n, here we have square root of n plus 1, here is eigenstate of the initiation operator, which is unknown right now, but we can assume that we know it, and it gives n plus 1. So if you plug here n equals 0, we get C sub 0 equals mu square root of 0 plus 1 equals C1, right? So basically mu. So if you know C0, then you know C1. If we do know, if you plug in n equals 1, we have C1 times mu divided by square root 1 plus 1 will be C2, right? No wise. But C1 is already known. So you can tell that it is mu divided by square root of 1 plus 1 will be 2. So this comes from here. And from C1, we are having mu divided by square root of 1 times C sub 0. So second expansion coefficient will be mu to which power?
Second.
Thank you. Divided by square root of 1 times 2. C sub 0. Right? So we can practice same procedure again and again. And we will find that the only two parameters, two things that we do not know, are the eigenvalue of initiation operator mu and the expansion coefficient C sub 0. The rest are expressed through it, right? So it's just micro work. Or we already got C2, u square 1 over 2. If it will be third coefficient, will be new third 1 times 2 times 3 square root C sub 0. And it's not complicated to predict that if you ramp up again and again, it will be eigenvalue to the power n, and here will be 1 times 2 times 2 times 3 n factorial C sub 0. So how do we get the C sub 0 coefficient? Any ideas?
Normalize the ground state wave function.
It's just music to my ears. So each state, whether it is eigenstate of any operator or it is an arbitrary state that has been created through some complicated process, is expected to be normalized, right? So if we express S state in the basis of continuous Cartesian position, then integration of the wave function square over the whole region should give 1. And if the wave function is expressed in a good basis, in discrete as expansion coefficients, then summation of all expansion coefficients squared should also give 1, right? So that total, in this course, we always have one particle. So summation of all expansion coefficients gives number of particles, or probability to find this one particle. How do we practice it? So we tell that 1 equals summation C sub n star C sub n, right? And it's mandatory. But we do have expressions for C sub n in terms of zeros expansion coefficient and eigenvalue. One is mandatory equals to u star power n square root in factorial C sub 0 star, right? So this was C sub n star. Objections? No. Okay. And now repeat the same. I am repeating the same thing without star. U power n square root n factorial C sub 0. Well, we can, and we need to solve for C sub 0. Right? We can put it outside of the summation because it is a common factor. And here we do have mu star times mu to which power? Right? Mu power n times mu power n will be mu times n. Not times, power n. Square root n factorial times square root n factorial. We can just remove square root, right? So, what does your calculus background tell you about this expression? Can you give the answer? Can we simplify it in such a way that we do not have summation of infinite number of terms, but we have some simple function? There are not too many simple functions. You may just blindly guess, and there is a very high probability if you that you will be right. Do not hesitate. Please guess some functions that you know. I will rename the mu star times mu as x, and then this writing will be 1 plus x over square root of 1 plus x square over square root of, not square root, just 2 factorial plus x third to 3 factorial, so forth, x power n over n factorial.
That's like a table.
Is it a Taylor series or?
Oh yes, we all know from our toddler's time what is Taylor series, right? Any function can be expanded as summation. You do not see it. Okay, here is 1 plus x squared over 2 factorial plus x3 over 3 factorial plus xn over n factorial. So any function or any good function can be represented as summation of polynomial functions of increasing order with some set of coefficients, right? Nothing clicking yet? Give me a secret sign if you already recognize the answer. Next year, more calculus should be included in this course. So what are these expansion coefficients? So I will write it once again. So it is coefficient function at 0 plus first derivative of function at position 0 times x plus second derivative of function at position 0 times x squared over 2 plus so forth, right? Taylor series. Let's cheat. Which function will at point 0 will be equal 1? I know you can ramp it up, but
Exponential.
yes. So see, very first guess does work. So it is one of the major findings of the human civilization that one can replace complicated functions and even simple functions by Taylor series. And exponential is this one. I'm absolutely sure I'm not the last one. This class is not the last instance in your time when you see this expansion. So this summation, based on this basic calculus, can be replaced by e to the power mu squared. That's it. And then you see that there is a connection between c sub 0 and mu, and you can solve for c sub 0. Okay, I was too excited to go over the material irrelevant to my notes. Even before we know c sub 0, let me bring it to your attention. On the nominator, you have mu to the power n, which is increasing function. If mu is big, then this will escalate. The denominator is n factorial, which will kill anything. It drops down very quickly, right? So if n equals 10, then this 1 divided by n factorial is 0. So we have two trends, one increasing, another is decreasing. Therefore, this distribution will look approximately this way. So the zeros first, second excited coefficient, excited state coefficient will be substantial, and as we go to infinity, to higher excited coefficients, we'll get nothing. And if mu is really small, then everything will decrease. If mu is equal 0, this state will coincide with ground state. Okay. Requesting expansion. Here is where we need to recall the calculus, right? And then we request that due to normalization, this zeros expansion coefficients times e to the power mu squared equals 1, right? So you divide everything by e to the power mu squared and take square root, which means just divide by 2. So what do we have? Before our object of interest, which we are very, very close to fulfillment of all promises. Object of interest, which is eigenstate of annihilation operator, before it was depending on two parameters, eigenvalue and zeros expansion coefficient. Now we express zeros expansion coefficient in terms of the eigenvalue, and it means it depends only on one parameter. So as soon as we know eigenvalue, this letter mu, we know each expansion coefficient. So we have this object ready. Come on. And when we plug it in, the C sub 0, then it is an eigenstate of the annihilation operator. In very, very soon, I think very beginning of the next meeting, and now we are approaching it really close, you'll see if this thing is expressed in the Cartesian projection, it will mean that wave packet of minimal uncertainty, the wave packet that is in shape equivalent to the ground state, can travel forth and back and mimic classical motion. So there are multiple realizations of this situation in the true world in physical chemistry. So like femtochemistry that gave Ahmed Zewail a Nobel Prize for pump probe result experiments in 1985, where one promotes from one potential energy surface to another by femtosecond laser and then follows details of chemical reaction in time. This is a state that governs generation of light in lasers. This is a state that generated in the active vibrational mode if it is irradiated by infrared laser, and we can come through multiple, any molecule excited by femtosecond pulse generates this state in the excited state vibration. So, but if you look in the basis of eigenstates, so this is eigenstate, this is the factor that grows and then drops, and here is the normalization. Where is time? Where? No, there is no time. But we do have time in our real life. And the function also wants to have time. How do we edit? How we propagate? How we propagate any quantum state forward in time? No tricks, no evolution operators, no computer codes, just simplest possible thing. If we know a wave function as expansion in the basis of eigenstates, how does it evolve in time?
E to the negative I et.
Mm-hmm. E to the negative I. What else?
I think it's the energy times time.
Which energy?
The energy of the state that you're at, so E sub k in this case.
And maybe divide by h bar
Oh,
to keep the
Oh, that's-
dimensionalities, right? So as soon as we do this trick, you can tell that it will be time dependent eigenstate of annihilation and independent state. Okay, and now it's a time of use for main outcome of the time independent Schrödinger equation for harmonic oscillator. What is the energy of state K? Please consider to review it, memorize it, even if I do not design a way to check. You know, on this is probably one of 5 or even 3 equations that you want to memorize after the course. So for harmonic oscillator of frequency omega, what is the energy of state K? Does it depend on the frequency?
Yes.
Yes. Probably for dimensions it needs Planck constant. Right? Does it, since we have K, does it depend on K? K. What if K is equal 0?
Then it should be 1/2.
Yes, so there is a 0 phonon energy. Even if at absolute 0, the phonon modes have some 0 motion. K plus 1/2. Right? So we can plug this expression into here and get the time evolution of this state of interest. So mu of t equals normalization, summation, u times k, square root of k factorial, e to the power minus I or h bar t, and here I put in this corner it doesn't copy, the stylus doesn't copy. H bar omega k plus 1/2. So h bar cancels here and there, and you see the thing proportional to 1/2 is the same for any term in summation, so we can put it up front. U of t e to the power minus I omega t divided by 2 e minus mu squared over 2, those were factors, and then times summation k, 1 square root of k factorial, and then here we have mu to the power k times e to the power minus I omega k t. So k is factor, is not the subscript. Here is a little, well, I wouldn't say magic, it is a little optimal mathematical trick. It is based on the rule of multiplication of exponentials. So if you do have e to the power a times e to the power b, it is e to the power a plus b. Right? Or if you have e to the power 2 omega, it is equivalent to e to the power omega second power. It is not visible again. E to the power 2 omega can be replaced by this expression, right? 3. But here we do have the overtones, the frequency, the higher line excited state accumulates phase quicker and quicker, proportional to its index, right? Frequency doubles, triples, quadruples. Omega times 1, omega times 2, omega times 3. But we can assume that, not assume, we can think that it is e to the power omega, well, I omega t times, not times, in the power k. Right? No cheating. Pure math. So this exponential can be replaced to e to the power minus I omega t to the power k. This is great. This is really great. So now we do have standard phase accumulation factor that will be applied to each state, but in different power. But look here. Here we have this eigenstate to the power k. Here we have this phase accumulation factor to the power k. Let's meet each other. So that it will be mu times phase accumulation to the power k. Why? Which benefits? I'm impatient. We will roll forward, and then we will see that it will be coherent state again, but the eigenvalue will be time dependent. It will be accumulating phase. So do not be scared. This is just slow repetition of all things that we already discussed. So we make, instead of static base state, we let them accumulate phase. And then there is a phase accumulation up front for this zero phonon frequency. There is this stuff, and then we develop this equation in a form where each time we see eigenvalue, it is multiplied by phase accumulated factor. And then it is in the power, and then by functional form, we do see the same shape as we saw before we started any time dependence. So if we look onto this expression, we can just rename the multiplication, this phase accumulated eigenvalue, as mu bar depending on t, and then we will get back the same functional form of the eigenvector of the annihilation operator. Will it be eigenvector, eigenstate of the annihilation operator? Yes, because we've proved that this functional form matches. So any any complex number can be plugged in instead of mu. So even the complex number accumulating phase in this Euler type. And it will be still eigenstate of the annihilation operator. So how does this state changes in time if we are yet in the discrete representation? Well, if you go from time t to times t plus delta t, we will have the same value as it was in the past times little phase accumulation. Right? So if we propagate forward in time, we keep functional form, but we just change this parameter mu by phase accumulation. And this parameter accumulates phase with a pace equivalent to the frequency of oscillator, the main frequency of oscillator. So I'm going to finish in whatever seconds, but right now you may not realize how powerful you are, but you are. So from now on, you can do anything. You can predict any observables related to any oscillation. Next time when we will meet, we will just make our brain a little more content by showing something visual. Not computationally visual, but pen and paper visual. So you will see how this state evolves in time in Cartesian space. And if I do not follow the suggestion of Braden, and due date for the homework will be on Wednesday, then you will see coincidence between your computational homework and what we will develop in class. I'm open to discuss, but it will be a little benefit to see the things together. If you do not look onto visually pleasant things, if you already are comfortable with this quantum developments, this expansion covers most of the possible states of any harmonic oscillator in the real life. And if you do want to predict some observable, no matter which one, you can follow the standard prescription to find an observable. You select an operator and you take bra and cat of your state. So you take bra and cat of the state, put any operator in between, and you predict an observable. So anything related to harmonic oscillator can be predicted. And this state is general enough. So in fact, in real life, harmonic oscillators do exist mostly in three quantum states. One of the eigenstates, which is boring, one of the coherent states, and one of the thermal states, these states that you deal in thermodynamics. But right now we are two-thirds to cover anything. No, I will not answer during the class. Is it time to finish? Well, I think it is. Okay, thank you for coming and for your interest in the course. I look forward to see you on Wednesday, and please help me define your election, your votes about your preferences about research program.
Thank you so much.
Which one did you?
Hannah, thank you for getting the final and stuff moved to Wednesday.
Yeah, did you tell other people to email her?
I told everyone.
Okay, I figured.
I had 4 of your numbers, and then Megan, Gage, and Luke I had to email. But
And my other one was also like a.
sorry, I only have so many numbers.
Or no.
Yeah.
I'm not sure what that means. Yeah. I don't know. Might end up doing something solar cell related.
So I first started off with
project.
three, but then I didn't.
If I kind of do like both of those together, then I'd actually have like something.
That's why. That was my
Solar cell.
Yeah, no, because to be at the test on Tuesday, she was nice to postpone it. I'm so glad.
That's good. She was gonna have it on Wednesday.
Yeah, now, like, it's supposed to be today.
Oh, okay,
Yeah.
wow. That's still about.
And then